Okay, welcome back everyone. In this segment and the next, we're going to see how to actually build a SNARK. By the end of these two segments, you will see all the components that are needed to build a SNARK. So first, let's quickly review what we discussed in the last lecture. And you remember that the first thing we had to do was define a computing model. And the computing model that we use here is going to be an arithmetic circuit. Yeah, just remember that an arithmetic circuit is a circuit that's made up of addition and multiplication gates modulo p. And the arithmetic circuit outputs an element in a finite field, fp, which is a set of numbers 0 to p minus 1 with addition and multiplication modulo p. Now, the arithmetic circuit takes an input, a statement x, and a witness w, and as we said, outputs an element in the finite field f sub p. Now, in a pre-processing argument system, the first thing that happens is we pre-process the circuit C. So we have this setup algorithm that takes a description of the circuit C as input and outputs these public parameters. There are parameters for the prover and there are parameters for the verifier. Then the prover and the verifier both take some inputs. And what the prover will do is will produce some sort of a proof pi that says, I know some witness W that makes C of XW equal to 0. Yeah, and the verifier then decides either to accept or reject this proof just using the statement x. Again, recall, the verifier has the statement x but not the witness, whereas the prover has both x and the witness. Now, in the last segment, we saw a number of examples of what the circuit C could do. Just as an example of a circuit C, you can think of a circuit that proves knowledge of a hash preimage of the statement x. That is, the circuit C proves that the hash of w is equal to x, and the verifier, of course, knows x but doesn't know w, and yet the proof will convince the verifier that the prover knows a w such that the hash of w is equal to x. Yeah, that's just one example of a circuit C. If the hash of w is equal to x, the circuit will output 0, otherwise it will output non-zero. And again, the proof will convince the verifier that the prover knows a w such that hash of w is equal to x. There are many other circuits one can consider, for example, circuits that might verify signatures and many other things that the prover might want to prove to the verifier. So again, just reviewing the syntax for a pre-processing argument system, remember that a pre-processing argument system is made up of three algorithms: the setup algorithm, the prover algorithm, and the verification algorithm. The setup algorithm, as we said, outputs SP and SV. The prover will take X and the witness and produce a proof pi, and the verifier will take X and the proof and either accept or reject. We outlined a number of requirements for an argument system. The first requirement is that this proof system be complete, meaning that the honest prover will always produce a proof that the verifier will accept. The second property is what we call knowledge soundness, which means that if the prover is able to produce a proof that the verifier accepts, that means that the prover must know some witness W such that C of XW is equal to 0. We saw last time how to define this more precisely using an extractor that's able to extract the witness W from a prover that's able to convince the verifier. And just as an example, again, if we look at the circuit that says, I know a pre-image of X, I know a value W such that H of W is equal to X, and maybe W is in a certain interval, that would be an example circuit C. And if the prover is able to convince the verifier that it knows such a W, there must exist an extractor that can extract this W from the prover. And optionally, we might want the proof system to also be zero knowledge, which means that the proof along with X and SV should reveal nothing about the witness W. So these are the three high-level requirements we wanted for a pre-processing argument system. And then to make a SNARK, we have two more succinctness requirements. The first requirement is that the proof be short, meaning that the length of the proof pi should be its most logarithmic in the size of the circuit C. And the proof should also be fast to verify, meaning that the time to verify the proof should be at most, again, logarithmic in the size of the circuit C. Of course, we need to allow the verifier to read the statement X, so we allow the verifier to run in linear time in the size of the statement X. Now you notice this, I use this notation O sub lambda here. Lambda is always going to be used as a security parameter. You can think of lambda as typically set to be 128, but asymptotically we allow lambda to be another parameter, and really the size of the proof and the time for the verifier also needs to be polynomial in the security parameter lambda. But we are mostly going to ignore the dependence on lambda, which is why we put it as a subscript and primarily focus on the dependence on the size of the circuit C and the length of the statement X. Now, you notice because the verifier runs in time logarithmic in the size of C, the verifier cannot read the circuit C, but it has to be able to verify that C of xw is equal to 0. So someone must have had to read the circuit C, and this is why we do the pre-processing step. The pre-processing step basically reads the entire circuit C and produces a short summary of the circuit for the verifier. Yeah, so SV typically will be very, very short, and it, as we said, kind of summarizes the circuit C for the verifier. Okay, so now let's switch gears and dive right into how to build an efficient SNARK. So what's interesting is that there is a very general paradigm for building efficient SNARKs. This is not the only paradigm. There are other paradigms for building SNARKs, but here I want to specifically focus on one very general paradigm for doing that. And so the way we build a SNARK is by actually combining two very general concepts. The first concept is what's called a functional commitment scheme, which we'll define in just a minute. And the second concept is what's called an interactive oracle proof. Yeah, so the interactive oracle proof, an IOP, is going to be compatible with the functional commitment scheme. Again, we're going to define these two concepts in just a minute. We're going to put these two things together, and out will come a SNARK for general circuits. So let's see exactly what each of these concepts mean. We'll start with functional commitments, and then we'll describe what are interactive oracle proofs. But I do want you to remember that the SNARKs that we will be constructing in these two segments follow this general paradigm of putting together a commitment scheme along with an interactive oracle proof, and those together give us the SNARK. What's interesting is that most of the cryptography happens in the commitment scheme. This is where all the cryptographic assumptions come up, whereas the interactive oracle proof is more of an information theoretic object, and we can prove its security without making any complexity assumptions whatsoever. So in some sense, we're combining a cryptographic object with an information theoretic object, and that's what gives us a SNARK. Okay, so let's dive right in and explain each concept in turn. We'll start with functional commitment scheme. So first, let's review what is a cryptographic commitment. So a cryptographic commitment basically emulates a physical world envelope. So imagine Bob wants to commit to some data to Alice. What Bob will do is he will put his data in an envelope and send the envelope over to Alice. Alice doesn't see what the data is, but she knows that at this point Bob is committed to the data because it's in the envelope and Alice is the one holding the envelope. Later, Bob can open the envelope and reveal the data to Alice, and Alice is assured that the data that was revealed is in fact the data that Bob committed to ahead of time. This concept is implemented by two algorithms, which we call the commit and verify algorithms. The commit algorithm is run by the committer Bob, and the verify algorithm is run by the receiver Alice. So the commit algorithm will commit to some message M using some random value R. So Bob will choose a random value R and commit to the message M using this randomness R. And this commit algorithm will output a short commitment string. It's actually quite important to remember that the commitment string is short no matter how large the message is. So the message itself could be gigabytes and gigabytes of data. The commitment string is going to be very short, typically something like 32 bytes. Later on, Bob can open the commitment to Alice by revealing M and R. Alice would then run the verify algorithm, giving it M, the commitment, and R, and the verify algorithm will say accept or reject. A commitment scheme has to satisfy two basic properties. The first one is called the binding property, which means that after Bob commits to some data, he can only open the commitment in one way. And the way we capture that is by saying that Bob cannot produce a commitment along with two different valid openings of that commitment. So that's the binding property of the commitment. And the hiding property of the commitment says that the commitment itself reveals nothing about the committed data to Alice. Yeah, so even though Alice received the commitment, she learns absolutely nothing about the committed data. And many of you might know that there's a standard construction for commitment schemes using hash functions. In particular, we're going to use a hash function that takes a message and some random string and maps it to the commitment space. And basically, the commitment function is defined as a hash of M, R. Remember that M is the data and R is the randomness, and that's how we produced a short commitment string. And the way we verify the opening of the commitment is basically Alice will just rehash M and R and verify that she got the commitment string back. And one can show that for a suitable hash function H, this is in fact a hiding and binding commitment scheme. So that's how we commit to data, but in our case, we actually want to commit to a function. So what does it mean to commit to a function? So first, we're going to fix some function family from a set X to a set Y, and the committer will be committing to some function in this function family. Now I'm going to change the name of the committer to the prover, because typically the prover will be committing to a function. And I'm going to change the name of the receiver to the verifier, because the verifier is the one who's going to be verifying openings of these commitments. So let's see what does it mean to commit to a function. So here the prover has some function in the function family, and he wants to commit to this function, and so he'll commit to the function using a short commitment string, which we'll denote by com sub f, and the verifier will store this commitment. Later on, the verifier is going to say, hey prover, can you please open the function you just committed to at the point x? What the prover will do is, of course, it will compute f of x, which we'll denote by y, and it will produce a short proof that proves that f of x is equal to y and that the committed function is in fact in the function family. And the verifier will verify this proof and either accept or reject. So you notice that what's happening here is that the prover committed to a certain function f, and later on the verifier can ask the prover to open the function at one particular point x in the domain of the function. The prover can then convince the verifier that in fact the committed function f satisfies f of x is equal to y, where the verifier knows both x and y. So this is what it means to commit to a function. The prover commits to a function and then later opens the function at one particular point. So let's see the syntax for this in a bit more detail. So first of all, for a functional commitment scheme for a function family f, first of all, we run a setup algorithm that generates some public parameters. This is a one-time operation that we just run at the beginning of time and never again. Then the prover can commit to the function f by running a commit algorithm. This produces a short commitment string com sub f, and that's a commitment to the function f in the function family. And this commitment should be a binding commitment to the function f. So once the prover commits to the function, the prover can no longer change its mind about what the function is. And the commitment scheme should optionally also be hiding, which means that the commitment should reveal nothing about the committed function. As we will see, if we're building a snark, we typically just need a binding commitment. It does not need to be hiding. But if we're building a zero-knowledge snark, often we might need a commitment that's both binding and hiding. But for a snark, a binding commitment is sufficient. Now, the important component of a functional commitment is the evaluation protocol. So the evaluation protocol is between, again, the prover and the verifier, where here the verifier has a commitment to a function f, and it has some values x and y in the domain and the range of the function. What the prover will do is it will take as input f, x, y, and the randomness for the commitment, produce a short proof pi. The verifier will take the commitment to the function, x, y, and the proof, and will either accept or reject the proof. So what are we proving here? So this eval system is itself going to be a snark for the following relation. What this proof pi proves is that in fact the function f at the point x evaluates to y, that the function f is in fact in the function family, and that in fact if we commit to f using the randomness r, we obtain the commitment string com sub f. So the witness for this relation is the description of the function f along with the randomness r. And the statement here, the public statement, here is the commitment string and the values x and y. So this is what a functional commitment allows us to do. It basically allows the prover to commit to a function, and then later on the prover can produce a succinct proof that the committed function satisfies f of x is equal to y. And again, the security properties should be that the commitment is binding and optionally hiding, and that the eval protocol is in fact a snark for the relation described here. And I'll briefly mention that the fact that the eval system is a snark means that there's an extractor that will extract the witness f and r from a successful prover. So now that we know what does it mean to commit to a function, there are three very important examples of function families that we might want to commit to. So the first example is what we call a polynomial commitment scheme. So what is a polynomial commitment scheme? Here we set the function family to be the set of all univariate polynomials over fp of degree at most d. Yeah, this is what this notation means. This is the set of all univariate polynomials of degree at most d. The prover can commit to some function in this finite set. And of course, later on, the prover can be asked to reveal the value of this committed polynomial at some point x. The second example I'll mention is what's called a multilinear commitment. So in a multilinear commitment, the function family is set to be all the multilinear polynomials in at most k variables. So what is a multilinear polynomial? It's basically a polynomial that's at most linear in each one of its variables. Yeah, so here's an example. You notice that this polynomial is linear in each one of the variables. None of the variables are squared or cubed. All the variables have degree at most 1. And again, the goal is to enable the prover to commit to a function in this function family. And later on, the prover should be able to open the function at a particular point. The third example I'll mention is what's called a linear commitment scheme. So in a linear commitment scheme, the set of functions is the set of all linear functions, which means that the prover will commit to some function that's parameterized by some vector v, and the function itself is defined as the inner product of v and u, which is what we wrote over here. So it turns out that different SNARK systems use different commitment schemes. Some of them use polynomial commitments, some use multilinear commitments, some use linear commitments. And depending on which commitment scheme we use, we end up with a different type of SNARK system. What's interesting is that these commitment schemes are equivalent to one another in the sense that they can each be constructed from the other. However, what I want to say here is that in some sense there's a strict ordering between these commitments in terms of generality. And what I mean by that is that a multilinear commitment is somewhat more general than a polynomial commitment in the sense that if I give you a multilinear commitment, it's actually very easy to build a polynomial commitment from it. And I'm going to leave it as an exercise for you to think about. Again, if I give you a multilinear commitment scheme, your goal is to build a polynomial commitment scheme from it. And you can do that directly and actually very, very efficiently. So I'll leave it as an exercise for you to think about how to do that. This is a good homework problem. And similarly, given a linear commitment, we can build a multilinear commitment from it. This is actually not difficult to see. And again, I will leave that as a homework exercise. So these different commitment schemes lead to different types of SNARKs. The SNARK that we want to construct here is going to be based on polynomial commitments. So from here on, we're just going to focus on polynomial commitments. Okay, so let's talk about a polynomial commitment scheme. I'm going to abbreviate that as a PCS. And again, just to remind you, a PCS is basically a functional commitment scheme for the function family of univariate polynomials of degree at most d. What this means is, again, the prover will commit to a univariate polynomial of degree at most d. And later, the prover can prove to us that the committed function f at the point u evaluates to v for some public values u and v. Now, what's important, again, is that this is a SNARK proof, which means that it's going to be very short. The proof has to be logarithmic in the degree of d. And verifying the proof should also take time, at most logarithmic in the degree of d. So we want to commit to a huge degree polynomial. The polynomial could have degree 1 billion. We'd like to commit to it using a very short string. And later on, we want to be able to open this polynomial at a given point, u, and the verifier should be able to verify that the polynomial was opened correctly in time at most log d. And this is all going to be done using a proof that's at most logarithmic in the degree, which again means that we're presenting the verifier with very short proofs that are very fast to verify. So we have many examples of polynomial commitment schemes. So for example, using basic elliptic curves where the discrete log problem is hard, this is the same algebraic structure that's used for Schnorr signatures. We can build a PCS from the bulletproofs system. It turns out this is not exactly a PCS. The proofs, the evaluation proofs will be very short, but verifying the evaluation proof will take linear time in D as opposed to logarithmic time in D. So this is not exactly a PCS, but it does produce very short evaluation proofs, and it's done based on a very simple algebraic structure, the same one that's used to construct Schnorr signatures. Another example can be built from bilinear groups. These are elliptic curves with additional algebraic structure called a bilinear map. And there are, in fact, a number of PCSs constructed from bilinear groups. The most famous one is what's called the KZG10. We'll talk about this one more in just a minute. This one requires a trusted setup, as we'll see in just a second. If we want to get rid of a trusted setup, there's another PCS from bilinear group called Dory. And Dory basically is, again, a very efficient PCS that eliminates the need for a trusted setup. We also have PCSs from what are called groups of unknown order. These are related to the RSA assumption, and the PCS that comes from such assumptions is called dark. And we will link to all these papers in the supplementary reading materials in case you want to see how all of them work. Finally, there is a PCS that's built from hash functions only using a mechanism called FRI. FRI is also the building block for the Stark system, and it can also be used to build a PCS. So as you can see, there are many, many ways to construct a polynomial commitment scheme. In this segment, I'll focus on the KZG commitment scheme because this is the simplest one to describe, and it's actually the one that's most commonly used. So let's see how KZG works. So the KZG system is due to Kate, Zaverucha, and Goldberg back in 2010. This is why it's called KZG, named after the authors. And it operates in a cyclic group of prime order P. So a cyclic group has a generator, which we'll denote by G. And the group elements basically consist of G, g plus g, which we'll denote by 2g, g plus g plus g, which we'll denote by 3g, and so on and so forth up until p minus 1g. Yeah, and p times g is going to be equal to 0. So if you're not familiar with what a cyclic group is, it's not the end of the world. Just think of it as a set of p elements where any two elements can be added. So for example, I can take 4 times g and 9 times g, add those elements together, and what I'll end up with is the element 13 times g. So this gives us a set of p elements where any two elements in the set can be added to obtain another element in the set. Okay, so let's see how the KZG system works. So first of all, we have to describe the setup algorithm that generates the public parameters. So the way the setup algorithm works is first we sample some secret element alpha in the finite field. And then the public parameters are actually going to be very simple. It's just going to be the generators, the first element of the public parameters. The second element of the public parameters is going to be alpha times g, then alpha squared times g, all the way up to alpha to the d times g. Remember, d is the bound and the degree of the polynomial that we want to commit to. So this gives us a tuple of d plus 1 elements. So really the public parameters consist of d plus 1 elements in the group. So that's how we generate the public parameters. And the important next step is whoever runs the setup algorithm has to delete this secret alpha and forget it forever. And this is actually why this is a trusted setup. We have to trust whoever ran the setup algorithm to delete this value alpha. If the value alpha is not deleted, if anybody learns what this value alpha is, they can actually create false proofs, meaning that they can commit to a certain polynomial and then convince the verifier that the polynomial evaluates to the wrong value at a particular point. And that will break all of our SNARK constructions. So we really have to assume that whoever that runs the setup deletes the value alpha. Otherwise, the verifier could be convinced that wrong things are correct. So that's the setup procedure. We generate this tuple of elements. So now let's see how the prover will commit to a particular polynomial of degree d. All we'll do is we'll take the polynomial that we want to commit to, evaluate it at the point alpha. Yes, so f of alpha is an element in the finite field. We multiply that by g, and that will give us a group element, and that's going to be our commitment. So our commitment is a single element in the group that we chose. So again, I want to stress this is kind of remarkable that we can take a polynomial of degree 1 billion and commit to this entire huge polynomial using a single element in the group G, which is a very, very short commitment. Usually this commitment string will be under 64 bytes. So we're committing to a degree billion polynomial using a commitment string that's at most 64 bytes. Now you should be asking, well, how does the prover actually compute this? To compute f of alpha, you need to know alpha. But didn't I just say that alpha has to be deleted so that nobody knows what alpha is? So how does the prover actually compute f of alpha times g? And the answer is this is basically where we use the public parameters. So what the prover will do is it will take the polynomial f and write it as a sum of powers of x, which is what a polynomial is. And the way it will compute f of alpha times g is it will just use the values in the public parameters. So in fact, the commitment string is going to be equal to f of 0 times h0 plus f of 1 times h1 plus f of 2 times h2 up to f of d times hd. Now, if you expand this out just a little bit, let's just plug in the values for h of 0. Recall h of 0 is equal to g, h of 1 is equal to alpha times g, h of 2 is equal to alpha squared times g. You notice that we get this summation down here, and if we take g out of the parentheses, we get f of alpha times g, which is in fact the commitment to the polynomial f. So you notice that computing the commitment using the public parameters can be done without knowledge of alpha, and that gives us the commitment f of alpha times g. So we see that basically using a linear number of group operations, the prover can commit to a polynomial f. One thing that I want to point out is that this commitment scheme is actually binding but not hiding. In fact, you notice there's no randomness that was used during the commitment process. And this is exactly because all we're building here is a binding commitment, but in fact, this is not a hiding commitment in the sense that the commitment string might actually leak some information about the polynomial f. But for our purposes, if we're building a SNARK, it turns out a binding commitment is sufficient. We actually don't need a hiding commitment. Nevertheless, I'll say that there's quite a simple extension of KZG, which makes it into a hiding commitment, but I won't describe that here. The next thing we have to do is look at the evaluation procedure. So how do we prove to the verifier that the committed polynomial f satisfies f of u is equal to v? So again, the verifier here has the commitment to the polynomial f. It has these values u and v, and it wants to be convinced that the committed polynomial f satisfies f of u is equal to v. So how do we do this? Well, we do that using the following observation. So first of all, observe that if f of u is equal to v, that means that u must be a root of the polynomial f minus v. Right? If we evaluate this polynomial f hat at the point f minus v, we'll get 0. So u must be a root of this polynomial f hat. Now, what does it mean that u is a root of the polynomial f hat? If you think back to your high school algebra days, you remember that if a polynomial f hat has a root at the point u, that means that f hat is divisible by the linear polynomial x minus u. Okay, so what does it mean that x minus u divides f hat? What it means is there exists some quotient polynomial q such that q times x minus u is equal to f hat, namely is equal to fx minus v. Okay, so this formula here is the critical formula that we're going to use to do the evaluation proof. Right? I'll say it again. The quotient polynomial q times the linear polynomial x minus u is equal to the polynomial f of x minus v. And in fact, this quotient polynomial q exists if and only if f of u is equal to v. So this will give you an idea for how to do the evaluation proof. What the prover is going to do is it's going to compute the quotient polynomial q of x. It's going to compute the commitment to the quotient polynomial. So it's going to compute the commitment string com sub q. And it's going to send this commitment string over to the verifier. And the commitment to the quotient polynomial q is going to function as our evaluation proof. What's amazing here is that the evaluation proof is, again, constant size. It's a single element in the group G. So we can commit to a polynomial of degree 1 billion using a single group element, and then we can open the polynomial at a single point, again using a proof that's only a single group element. This is kind of quite remarkable for a commitment scheme. How does the verifier verify this proof pi? Well, what the verifier will do is it's basically going to check that the two commitments line up. So it will take the commitment to the quotient polynomial q and multiply it by alpha minus u. Now, if you think about this for just 1 second, you'll see that alpha minus u times com q actually is exactly the commitment to the polynomial q times x minus u. Okay, so on the left-hand side here, the verifier computed the commitment to the polynomial that's on the left side of this equality. On the right side, the verifier takes the commitment to f, subtracts v times the generator. And again, if you think about this for a minute, you'll see that this is exactly the commitment to the polynomial f of x minus v. So on the left-hand side, the verifier constructed the commitment to the left-hand side polynomial here. On the right-hand side, the verifier constructed the commitment to the polynomial on the right-hand side. And if these two commitments are equal to one another, that means that this equality must hold. This follows from the binding property of the commitment scheme. So the verifier will accept basically if this equality holds. So again, what's amazing here is that the verifier is doing only constant amount of work to verify this condition. No matter what the degree of the polynomial is, it could be in the billions, verifying that the polynomial evaluates to v at the point u only takes constant work for the verifier. So again, some of you might be wondering, well, wait a minute. I said that nobody knows what the value of alpha is. This value was deleted. So how is the verifier computing alpha times com q? And the answer is actually that this is actually done using an additional algebraic structure called a pairing, which I'm not going to describe here. What the pairing does is it basically allows the verifier to check that this condition holds without actually knowing what alpha is. The only thing the verifier needs to know is the generator g for this step over here, and the value h1, which allows it to do this comparison without actually knowing what alpha is. So what's interesting here is that the verifier only needs two elements from the public parameters. Yeah, just g and h1. It doesn't need the huge public parameter string. It only needs these two elements, g and h1. So this is really important in a blockchain application because if we want to implement an on-chain verifier, the smart contract that's going to run the verification algorithm only needs to be told what G and H1 is, and that's going to be stored in the code that implements the verifier. And as a result, the code that verifies these proofs actually is not large at all. It only contains these 2 points, and that's enough to verify that the opening was done correctly. So this is the key idea of the KZG commitment that makes it so useful in building SNARKs and in blockchain applications. One thing I'll say is that computing the quotient polynomial when d is very large, when the degree of the polynomial is large, can be actually somewhat computationally expensive. And in fact, much of the work that provers that use this PCS do, in fact, goes into computing this polynomial Q and computing the commitment to this polynomial. So the lingering question in your mind should be, well, why is this PCS secure? Why is it binding? And why is the evaluation proof a SNARK? So it turns out that can be proved, but I'm not going to describe that today. Again, you can look at the supplementary reading material if you want to see how to prove that this PCS is secure. I will say that proving that the KZG PCS is secure relies on fairly strong cryptographic assumptions. Now, this KZG system has been used so extensively there are many generalizations of it. I wanted to mention that in fact KZG can be generalized to committing to k-variate polynomials, not just univariate polynomials. The one difference is when committing to a k-variate polynomial, the evaluation proof actually has k group elements in it as opposed to a single group element when committing to a univariate polynomial. That's one generalization. The other generalization I want to mention is what's called a batch proof. And again, this is a very important trick to remember. It comes up all the time in the SNARK space. And so a batch proof basically allows the prover to open many polynomials at many points all at once. So imagine the verifier actually has a bunch of commitments, let's say commitment to n polynomials. And the prover wants to prove that each of these polynomials evaluates to certain values at certain points. Yeah, so there are n polynomials, and we want to open each of them at m different points. Naively, this would take n times m KZG evaluation proofs, so n times m group elements. But it turns out using these batch proofs, it's actually possible to prove all these facts using a proof that only takes either 1 or 2 group elements. So we can take like n times n evaluation proofs and sort of batch them into a single very short proof that contains only 1 or 2 group elements. Okay, so again, I want to emphasize this is a very important trick that's used to shrink SNARK proofs and comes up all the time. So that's our description of the KZG commitment scheme. However, I did want to remind you that KZG requires a trusted setup. Remember, whoever runs the setup algorithm has to delete alpha at the end of the setup procedure. And also the public parameter size is linear in the degree of the polynomial we want to commit to. If the polynomials we're committing to are in the billions, we are going to end up with public parameters that are actually quite large. So the Dory commitment scheme actually solves many of these problems. First of all, it has transparent setup, so there's no secret randomness in the setup procedure. In fact, there is no setup procedure. Anybody can run the setup procedure for themselves. So there are no public parameters and there are no secrets that are needed for generating those public parameters. The commitment string is still a single group element, just like in KZG. The evaluation proof and evaluation time is a little bit worse than KZG. Remember, in KZG, the evaluation proof and verification time were constant. Evaluation proof was 1 group element, and verification time was a constant number of group operations. In Dory, this is replaced by logarithmic proof size and logarithmic verification time, which is still quite good. So I just wanted to mention that Dory exists as a possible replacement for KZG. Proof size and verification time is not as good as KZG, but the benefit is that we eliminate the trusted setup and the public parameters that are generated by the trusted setup. Okay, so that's all I wanted to say about polynomial commitments. And now we can switch gears and talk about the second component that's needed to build a SNARK. Remember, we have our polynomial commitments. We're going to combine that using what we call a polynomial interactive oracle proof, or a polynomial IOP. And these two things together will give us a SNARK for general circuits. So let's define what is a polynomial interactive oracle proof. So again, we're going to fix our computing model to be arithmetic circuits that have addition and multiplication gates mod p, and that take a statement and a witness as input. And let's look at a particular statement x. So a polynomial IOP is basically a proof system to prove that the prover knows W such that CXW is equal to 0, but the proof works in a very specific way. And so the first step of the proof system is again to pre-process the circuit C. So we have our setup algorithm that will pre-process the circuit C and output parameters for the prover. It's also going to output parameters for the verifier, but the parameters for the verifier is a bunch of polynomials. Okay, so here I denote these polynomials f of 0, f sub minus 1, f sub minus 2, and so on and so forth. It's convenient to index them by negative values, as we'll see in just a second. Now, SV only contains commitments to these polynomials, which is why we write the polynomials in a box. Yeah, so a commitment to a polynomial will denote by a polynomial in a box. And here, basically, SV just contains a commitment to s plus 1 polynomials. So that's the first step of the poly IOP. Later, when a statement X and a witness W are chosen, the prover will convince the verifier that it knows a W using the following interactive procedure. First, the prover will send a commitment to some polynomial to the verifier. The verifier will choose some random value R1 in the field FP and send this R1 back to the prover. Remember that this arrow means choose an element at random from the set FP. Then the prover will send a commitment to another polynomial. The verifier will choose a random R2 and send that to the prover, and so on and so forth, until finally the prover commits to its last polynomial. And finally, the verifier is going to run some verification procedure that takes as input the statement X and all these random values that the verifier generated, along with the ability to query the set of polynomials at any points of its choosing. We have here commitments to the polynomials in SV and commitments to the polynomials that were generated during the proof itself. And the verifier can basically ask the prover to open any of these polynomials at any points of the verifier's choosing. And so based on all this data, the verifier will decide to either accept or reject the proof. So again, I want to emphasize that what happens in a polynomial IOP is that the verifier sends a bunch of random values to the prover. The prover correspondingly commits to a bunch of polynomials. And then later on, the verifier can ask the prover to open these polynomials at a number of points. And based on that, it decides whether to accept or reject. Now, you might be wondering, what is the point for the verifier to send random values to the prover? The prover could just generate random values on its own. But the point is that these random values are chosen after the prover commits to certain polynomials. Yeah, you notice, for example, R2 is only chosen and sent to the prover after the prover commits to F1 and F2. At the time that the prover committed to F1 and F2, it does not know what R2 is. And that's very important to prevent the prover from proving a false statement. Okay, so that's syntactically how a polynomial IOP works. And as usual, we want the polynomial IOP to satisfy a number of properties. It has to be complete, which means that the verifier will always accept the interaction with a valid prover. It has to be knowledge sound, which means that if a prover P star is able to convince the verifier with some probability, there's an extractor that will extract the witness from the prover. And you notice here the extractor will basically use the statement as well as all the polynomials that the prover committed to be able to do its extraction process. And optionally, if we're trying to construct a zk-SNARK, then we would want the polynomial IOP to be zero knowledge, meaning that all the values that were sent to the verifier reveal nothing about the prover's witness. Okay, and now we can see sort of what the resulting SNARK will look like. So we'll parameterize the polynomial IOP by two values, t and q. T will be the number of polynomials that the prover will commit to during the interactive phase. And q will be the number of evaluation queries during the verify procedure at the end of the proof. This is basically the number of points at which the prover has to open the committed polynomials. And what's interesting is that usually T and Q are actually quite small. That is, the prover only has to commit to like 3 polynomials and then open them at 3 points, and that's it. So typically, as we'll see, we can build polynomial IOPs where T and Q are really quite small. And now you can sort of see what the SNARK looks like. The prover will basically send T polynomial commitments to the verifier. Later on, the verifier will open these polynomials at Q points. And then the verifier will decide whether to accept or reject. Now, you're probably wondering, what I just described in the polynomial IOP is an interactive process between the prover and the verifier, whereas a SNARK is supposed to be non-interactive. So how do we convert this interactive process into a non-interactive process? Well, we can do that using a general transformation called the Fiat-Shamir transform that makes interactive proofs of this nature into non-interactive proofs. So the Fiat-Shamir transformation is a general way to convert this type of interactive protocol where the verifier just contributes public randomness into a non-interactive protocol. So we will convert the interactive process into a non-interactive process using this Fiat-Shamir transformation. And now you can see kind of the parameters of the final SNARK that we're going to end up with, where the proof itself is going to contain T polynomial commitments plus Q evaluation proofs. The verifier's time is going to be dominated by verifying these Q evaluation proofs, and the prover's time is going to be dominated by the time to compute T commitments and to generate Q evaluation proofs. And since generally T and Q are really small, you can see that the verifier's time is basically constant, meaning it's independent of the size of the circuit being proved, and the length of the proof is also constant, again, independent of the size of the circuit being proved. So now the only thing left to do is basically to construct a polynomial IOP, and that's exactly what we're going to do in the next section. So by the end of the next segment, you'll see how these polynomial IOPs work, and then combining a polynomial IOP with a polynomial commitment scheme like KZG will give us a SNARK. All right, so I'll see you in the next segment. Bye, everyone.